Okay, so today's I'd like to talk a little bit about the intuition behind the OLS estimator. So we know that, to begin with, we know our vector y is equal to the matrix x dot beta, vector beta, plus some arrow vector mu, which is our arrow term. And if you are familiar with linear algebra, then you will immediately realize that this part x dot beta is actually going to belongs to the column space of x. Okay, so in case you don't know what is column space of x, just some quick reminder. So this is actually going to be a set which is all the vector of x dot beta. Let's say use another symbol, x dot b, where b can be any vector that belongs to Rk, because we know that x is actually a n times k matrix. Okay, so let's try to draw it out on the picture. So let's say we define our column space of x. Let me use a different color. So this is our column space of x. And I know it looks like it is on a 2D plane, but actually this column space of x belongs to Rn, since we have n different row, well, n different data, okay? But since I cannot really draw it out on this 2D paper, so this is a little bit abstract, but I hope you can understand the idea. And also we have our vector y, which is kind of outside of this plane, of this column space of x. This is our vector y. And also notice, don't get mixed up between this vector y and our regression line. So this is not our regression line. It's not the same thing that we introduced in the single variate cases, not the regression line. Okay, this is literally just a vector, and this is also a vector belongs to Rn. Okay, so now this x dot beta can literally be any vector that is inside this column space. It could be this vector, let's say. It could be this vector, it could be that vector, it could be any vector. And also, according to this vector relationship, if we connect this 2 point, we will find that this vector, I'll use the dot line, this vector is actually going to be our vector mu. Okay. So now the problem becomes, let's say this is our x dot beta. Okay. So now the problem becomes we want to find some beta so that this x dot, let's say that's our OLS beta, and that will give us, this vector will give us, remember in the beginning of the series we defined the OLS estimator. It's a vector that can give us the minimum, the smallest value of the sum of mu I square. So that's literally by definition, okay. And what is the sum of mu I square? So if we expand this sum, then we know that this is equal to mu 1 square plus mu 2 square all the way to mu n square. And this expression is exactly the definition of the square roots of our vector mu. The square roots of the magnitude of the vector mu. So in other words, it is a distance. It is the length of this vector, okay, this dotted vector. So now the problem simply becomes what the vector, so that the magnitude of the mu can be as small as possible, okay. So then if we know some basic geographic knowledge, we would know this magnitude of mu will be the smallest only when this vector is perpendicular to this column space of X. So in other words, when the vector mu is perpendicular, so this is going to be a right angle, and this vector will be our X dot OLS estimator. Okay, and this will be our shortest magnitude of mu. Okay, so at this point, again, if you are familiar with some linear algebra knowledge, you should also realize that this vector is also the projection of our vector y on the column space of X. And in linear algebra, we know that there's a special matrix we call projection matrix. That if we time that projection matrix, let's say it's a P, if we dot y with this P, and it will just give us this vector right here. Okay, and this vector is exactly the vector we just find out, which is our X dot OLS beta. Okay, and what is this P? Px. So in linear algebra, we know that this Px is equal to X dot X matrix dot the inverse of X transpose dot X dot X inverse dot Y. So just by comparison, so we find out this part should be this OLS estimator, which is exactly the same results as we already derived in the last video. Now we also find out the OLS estimator by using some geographic relation. And here are also some very interesting results. So if we substitute this expression back into our y, then we have our vector y just going to be equal to the projection matrix dot vector y plus our mu. Okay, so that the mu is going to be equal to the y minus projection matrix dot y, which is some identity matrix minus projection matrix of X dot our y. And then we're going to define these things as our M matrix. So we have the relationship. So we have the relationship of this M and M matrix and P matrix, which is M matrix plus P matrix. It's just going to equal to some identity matrix of n times n. So this is some important results that we're going to be using in next videos to prove some other properties. Okay, so this is about this videos, and I hope through my demonstration you can probably have a clear understanding of the OLS estimator. So I will see you in the next video.